Hello everyone. For this video, I'd like to discuss the method of Lagrange multipliers, which are symbolized with a Greek letter, like many technical variables. In particular, the method of Lagrange multipliers involves a specific set of equations, which is that the gradient of x, y, z is exactly equal to the Lagrange multiplier multiplied by the gradient of g of x, y, z, and that g of x, y, z by itself without a gradient equals a finite value k. The symbol for the Lagrange multiplier is formally denoted with an upside down y, which is known as lambda. So we would apply this as in, find the dimensions of the box with the largest volume possible if we want the surface area to be exactly equal to 64 square centimeters. So we see the function we want to optimize or find the maximum or minimum of is x times y times z, which is the geometric formula for the volume of the box, and the surface area is given as 64. So we set the formula for the surface area equal to 64. And since we have a common factor of 2 on everything, we can divide both sides by 2 to get 32 on the right hand side instead. So now that we know exact formulas for f and g, we can use the Lagrange multiplier method given earlier, which would be partial derivative of f with respect to x equals lambda times partial derivative of g with respect to x, and we do the same thing for the y and z components. And we see, fortunately for us, the second constraint of the Lagrange multiplier method, that g must have a finite value of k, was already given to us in the definition of the problem, where the value of k is 32, or more technically 64, where 32 after simplification. So now we can see, with some creative thinking, that the volume is exactly equal to 3 separate equations at the same time, and we multiply the Lagrange multiplier formula by the dimension that we did not already get by computing the partial derivatives. So now we have a 3 equation system, and we can see, because we derived a way of making the system equal to one thing 3 times, we can substitute in the right hand sides of each equation relative to each other. So when we do some rearranging after setting the Lagrange multipliers equal to each other, we see the Lagrange multiplier of x times z minus y times z equals 0. So when we solve this by factoring, the Lagrange multiplier must either be exactly 0 or x times z must be equal to y times z. But we see logically the Lagrange multiplier cannot have a value of 0, because that would mean the dimensions would be 0, which does not work if we want to have a box. By similar reasoning, with the second solution, we can cancel out z, because we know that z cannot be equal to 0, as the box must have some height. So we logically conclude that x must be equal to y, and we can see if we do a similar thought process, but we set the third equation equal to the second equation instead of the first one, we get z equals y. So now we can safely conclude that y squared plus y squared plus y squared equals 32, so that y must be exactly equal to positive or negative square root of 32 over 3. But we discount negative answers for the same reason we discount answers of 0, namely that it wouldn't make any physical sense. So we see in conclusion, all of the dimensions are equal to each other and equal to a specific value, which is 3.266, approximately. However, before we conclude that this is our final answer, we should test it. We do this by plugging in all of the numbers for x, y, and z, which is simply that one number, for the volume formula, seeing that the volume is this value cubed. So we now choose an arbitrary set to compare this to by stating x equals y equals 1, and when we compute this, we get z equals 31 over 2. And we know 31 over 2 neatly simplifies to 15.5, So we can conclude, based on this, that we have definite evidence that the volume we computed with Lagrange multipliers is the absolute maximum, and therefore is the optimal volume for the surface area given. Now that we have seen how the Lagrange multiplier method works, we can transition from applications of multivariable derivatives and toward conceptual definitions and formulas for multivariable integrals, starting with a two-variable integral called the double integral. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.